proved a theorem in our last class, and I gave an exercise, and the proof was -1. Okay, let me change the color. -1 times u is equals to -u. So we are going to prove this. I said this as an exercise in the last class. So the proof is simple, but you have to go through the proof to recognize all the steps. And it was like, so -1 times u is equals to -u, and this can be proved like -1 times u is equals to -1 times u plus 0, right? And this is equals to -1 times u plus u plus,
put a vector sign on 0 or
yeah, so
you're right, it was not trivial. I could do it finally.
minus u. Then this is equals to so -1 times u plus 1 times u plus minus u vector, and so this is -1 plus 1 u vector plus minus u vector. So this is simply 0 times u vector plus minus u vector, right?
So you proved in the previous class, right?
Yeah.
0 times u vector is the same.
Yeah. In the previous class, I proved that 0 times u is equals to 0. So then this is just simply minus u. And this is the proof of this. So there are some other proofs like yeah, I think I also told you to prove this one. C times 0 vector is equals to 0 vector. Okay. And there are some other proofs like, so unique additive identity. Identity. So that means there is only one 0 here. And how can we prove that? Do you have any idea? So in the axiom, it is not says that there is only unique additive identity.
We assume two unique
Yeah.
identity, and then we show that both are equal.
Yeah. So, but how do you do that? So I can start with
Set axiom, empty set axiom, they have this previous proof and also geometric. I'm talking about the
no now.
empty set
Yeah.
Empty set way. There is thing called there is only one. There's theorem called only one unique empty set. Right? I'm talking about axiom empty set way. So there we assume that there are two empty sets, and then they can prove that these two sets are actually one.
Yeah, that is the axiom of the axiomatic set, ZFC theorem.
From the axiom, they make the theorem.
Yeah.
Like there is only one unique.
But I'm not saying that here. I'm saying
But his idea is to choose two
Yeah.
identities, and you have to prove that they are the same.
yeah. So
By using your axioms or vectors.
yeah. So this is just simply if I take 0 and 0 prime are the additive identity, Then so since these two are the additive identity, so I can start with 0 prime, and this is equals to, yeah, 0 and 0 prime. So then 0 vector prime is equals to um, sorry, 0 vector prime plus 0, but 0 vector prime is also the additive identity.
Plus 0 vector.
Yeah, sorry. So that means this is also a additive identity. That means this is equals to what? This is 0 vector, right? These are simple proofs, so I'm not going to do all of this here. Okay, so one other problem you mentioned. So I'm considering the problem number 3 of Hoffman coins. And the problem is, so what was the problem? Okay, C3 is the vector space, and the field is C, complex number. So I'm considering the C3 vector space, this, and the ground and the field, underlying field is the complex number. Okay. So the problem is, if I take C1 1 0 minus 1 plus C2 0 1 1 plus C3 1 1 1 is equals to some C1. Can I have the problem?
Sure.
It is not. So the problem is, if C is the field of complex number, which vectors in C3 are linear combination of 1 0 minus 1 0 1 1 and 1 1 1. So this is the problem. This is problem number 3. Thank you. So how can you show that which vectors are the linear combinations of these 3 vectors? So to do that, what we can do is we can multiply this. So what is the definition of the linear combination?
Scale and add.
Yeah, so I can do like C1 times 1 0 minus 1 plus C2 times 0, 1, 1 plus C3 times 1, 1, 1, and then this can be equals to some C1, Z2, Z3. Okay, so from this what I can do is I can construct a system of linear equation, right? And the system will be like there is a C1 plus plus C3 equals to Z1. Then C2 plus C3 is equals to Z2 and minus C1 plus C2 plus C3 equals to Z3. So this is an inhomogeneous system of linear equation, right? And in our one of a previous class, we proved that not every inhomogeneous system has a solution, right? So there are conditions that needs to fulfill so that a inhomogeneous system can have solution. But so I can do I can construct the augmented matrix from this system, and this is 1, 0, 1, Z1, then 0, 1, 1, Z2, minus 1, 1, 1, Z3. So this is the augmented matrix, right? And what I can do is, so and for the first row, this is already the leading one. So I don't need to do anything here. But in this column, there is a minus 1. So I can add this row and this row. So then it will be 1, 0, 1, Z1, 0, 1, 1, Z2, and this is 0, 1, 2, Z1 plus Z3, right? Then, so for the second row, this is again the leading one. So what I can do is I can make this 0, and to do that what I need to do is, yeah, so the operation will be minus 1 times R2 plus R3 equals to R3 prime. Then this will be 1, 0, 1, Z1, 0, 1, 1, Z2, 0, 0, 1, and Z3. Sorry. Z1 plus Z3 minus Z2. Right? Now, for the last step, can you conclude something from this augmented matrix?
Solution.
No solution. Why is that? Yeah, there will be a solution because there is no condition for the this, right? Is it clear? Why is that?
So there will be a solution. Right?
Yeah.
So 1, 1, 1, 3, next 1, 3, 0.
Yeah.
So all this equals 0, right?
So if this is equal to 0, so if this is not 1, this is simply 0, then I'll say it like z1 plus z3 minus z2 is equals to 0.
Right.
If this is 0, then the this has to be satisfied, then the system will have solution. But in here, this is not 0, this is
1.
1. So there is no restriction to have a solution in the system.
That's why there is no solution.
There is a solution.
There is solution.
Yeah.
So if it is 0, then there is no solution.
Then this arbitrary parameters z1, arbitrary elements comes from the field z1, z3 minus z2. This is equal to 0. This has to be satisfied, right? If so, I said this z1, z2, z3. These are arbitrary numbers, right? And there is no restriction on z1, z2, and z3. So I can choose anything for z1, z2, and z3. So if this 1 is not 1 but 0, then z1 plus z3 minus z2 has to be 0 to have this system solution, but not here, because here there is a leading one, right? So that's why this system has a solution.
So, if you let me comment on this situation. So, to understand it a little better, you can choose Z1, Z2, Z3 to be some complex numbers. Suppose you choose Z1 to be I, Z2 to be I, and Z3 to be minus I, or maybe something else. Okay? So that you have a complex number on the right hand side. Z1 plus Z3 minus Z2. I mean, the right hand side, the right hand corner of the third row, there is a non-zero complex number on the right hand side. And the last equation, if that one was replaced by 0, then the reduced matrix tells you that 0 times C1 plus 0 times C2 plus 0 times C3 is equal to that complex number, right? Which establishes the fact that 0 is equal to some non-zero complex number. Because 0 times C1 plus 0 times C2 plus 0 times C3 is 0. So you have the situation 0 equal to some non-zero complex number, which cannot be a fact.
Sir.
So which means nothing.
Yeah.
So which tells you that it is not possible. So it is an inconsistent system. But as long as you have one there, you can further reduce this, augment this reduced matrix into a low reduced echelon form by making that one above those two entries 0, right? You can go to make them 0. And if you make them 0, then it has a unique solution.
Yeah.
Meaning that C1 is equal to that number, C2 is equal to that number, C3 is equal to that number.
Okay, so what Sir was saying is I can, so let me write it explicitly. So I can write it 1, 0, and 0, z1 minus z1, okay, so minus z3 plus z2, then 0, 1, 0, 2z2 minus z1 minus z3. in the last row is 0, 0, 1, z1 plus z3 minus z2. So this is the final row reduced echelon matrix, right? So now if I write the system again, this is simply C1 is equals to minus Z3 plus Z2, then C2 is equals to 2 Z2 minus Z1 minus Z3, and C3 is equals to Z1 plus Z3 minus Z2. So this system, let's say this is system 2, and this system, sorry, they have same solution, right? These two systems have same solution. So and from this we see that C1 is equals to Z3 minus Z2, and C2 is equals to this, and C3 is equals to this, right? But we choose Z1, Z2 and Z3 are arbitrary numbers. So that means you can, so that means this Z1, Z2 and Z3, this is the element of C3, right? And you can take the linear combination of these two vectors, this and this, and you can reach this arbitrary vector which is in C3, right? That means this problem, it says that if C is a field of complex numbers, which vectors in C3 are linear combinations of these three vectors. So all the vectors in C3 are the linear combinations of these three vectors, right?
So all the vectors.
Yeah. So because this Z1, Z2, Z3, you can choose any number for, right? Okay. So this is the solution for this problem. Okay. So now, so there is this one example I want to consider again.
You already defined span.
Yes. I didn't even define the subspace. So okay, two other examples. If empty set is a vector space, is it a vector space?
No,
Why is that?
I don't know, it doesn't feel like so it is
So
scale.
is it a vector space over any field?
The action don't match the field of the scalars. So it is one field, right?
Is it?
No.
Why is that?
It doesn't have a set of view objects.
Yeah, I don't understand. Can you speak a bit louder?
The action is required to be a vector space. It doesn't satisfy us.
Which one is not satisfying? Yeah.
Action 2.
Axiom
In
2.
the second action, a set view of objects called vectors, right?
Yes,
So
it has
that's
to
in the
be
vector space.
negative of the where is it?
But so let me give you another example. Is it a vector space?
Is it a vector space?
No,
Yeah.
it's not.
It is not? Why is that?
Inverse is a vector space.
No. It is a vector
It
space.
is a vector space. So it is a vector space.
It is a vector
It
space.
is a vector space.
It is a vector space.
It is a vector space.
Yeah, you are correct. You have to present the logic by means of which you are correct.
Yeah.
So the MZ is not a vector space, and the zero vector
It is a
consisting
vector
of only one vector is a vector space. Why is that?
Fulfills actions, so which actions fulfills, right?
Yeah.
So does it have to fulfill all actions, right? All 8 actions?
Yeah.
All 8 actions. So maybe then we have to go through the list, right? Is a field of scalar 0?
So remember the example that I gave you in the introduction class earlier, when I said that there is a statement that all the cell phones in this group are turned off.
Cell phones.
All the cell phones in this group are turned off. But in our case, there is no cell phone in there. Is the statement true for our case? Suppose there is no cell phone in the room.
But then it's
What do you do? So I think that
then it is not a statement.
no, it's a statement that all the cell phones in this room are turned off, but there is no cell phone in this room. Is this statement true for this room? Did you understand the question?
Then it is true.
No, not switch off. All the exactly, switch off. All the cell phones in this room are switched off. But there is no cell phone in this room. Is this statement true for this room?
Then it is true for this room.
It is true for
It's
this
true.
room. Such kind of truth is called vacuous truth.
Vacuous.
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 Vacuous truth means that you cannot disprove it.
Right. Okay, vacuous.
So in order to have the vacuous truth situation, you need something like for all type of things. But for the empty set, for all type of axiom, where there is for all elements, they are all vacuously true. But when there exists, that is not vacuously true, because there exists statements tells you that there exists an element. But in your case, in the empty set situation, there is no element. So that is false. There is a very subtle situation happening here. You need to understand. So when there exists type of statement, it means that you have to find an element, at least one element. But there is no element in your set. So this is false. And when one of your axioms is false, this is not a vector space.
Do you mind if I rephrase what you suggested? It means that the requirement is this phone needs to be switched off. So if there is no phone, it fulfills the requirement. Is that what you mean?
It is a vacuous kind of satisfaction of that. It vacuously satisfies the statement. That's one. So this is a very important fact. For the zero vector, it is a vector space because the reason that fails for one of the axioms asks you to find for the existence of the additive identity, the zero vector. That is good here, right?
Yeah.
And for every element, there exists an additive inverse. That is also fulfilled. Zero is its own additive inverse. Is there anywhere else there exists thing appears? in any of the axioms, is there anywhere else there exists appears?
There exists in the issue. I don't know.
These are the two cases where there exists appears, right?
In the vector space, I think they have around 8 issues.
Yeah, but only two existence action.
In only two cases there exists appears. Do you understand what I mean by there exists? For there exists an additive identity. So such type of axioms are, I'm calling them like which
Yes, only in C and D there are 2 places.
Yeah.
and both are satisfied for the zero vector. That is why it is a vector space.
But the vector space are all 8, no?
Yeah,
Yeah, but all others are satisfied.
all other already satisfied.
Oh, vacuum. Oh, okay.
All others are satisfied vectors.
First, we have to go for vectors.
Yeah.
So this is mathematics. Mathematics is something.
That is very It's so certain that I cannot catch.
No, but you will get it. Get used to it. Once you play with these things, you will get used to it.
Okay, so another example. So let infinity and minus infinity denote two distinct objects.
So these two examples are very important. According to the linear algebra, the zero vector example and the empty set example are very important examples. These actually helps you arguing in mathematics. These are extreme examples that are very powerful according to me. Even that example is even more powerful, the zero vector example, when you study the dimension, the concept of dimension of a vector space. You see that the dimension of that's the only example of a zero dimensional vector space. That's the zero. And you see that these examples tells you that it is a vector space. None of those elements are in its spaces.
Yeah.
So when you study, so please get back to this example when you define
Because
basis as dimension.
yes, sir. And even when we are considering the when we will consider the subspace, we are going to define something like every non-empty set of a vector space. So let infinity and minus infinity denote two distinct objects. Sorry, let infinity and minus infinity denote two distinct objects, neither of which is in neither of which is in R. Define addition and scalar multiplication.
These are infinite, right?
Yeah. So
It's better not to think them as infinite.
yeah, these are just
Think of them
distinct.
as elements.
Just elements.
Just elements.
And that's why we write something like minus infinity, comma infinity, and these are not closed.
But we pronounce infinity.
You pronounce infinity, but just for the moment we think them as.
That means the real number doesn't have this element minus infinity and plus infinity.
Because ideally you cannot add or subtract infinity from infinity. But we are doing that because we are considering them as elements.
Elements. Yeah. Okay. So multiplication on R union infinity union these elements as you is good guess. Notation. So t times infinity, so this elements is 0 in this if t is less than 0, if t equals to 0, and t is greater than 0. And t times minus infinity is equals to infinity 0 minus infinity. If t is less than 0, t equals to 0, and t greater than 0. And t plus infinity is equals to infinity plus t equals to infinity, then t plus minus infinity is equals to minus infinity plus t equals to minus infinity. Then infinity plus infinity is equals to infinity, minus infinity plus minus infinity is again minus infinity.
I have a question.
Yeah, sorry.
So when you are defining multiplication of t with minus infinity and
Yeah.
multiplication of t with infinity,
Yeah.
that t
So-
is in the field.
Yeah.
But when you are adding t to infinity, it is in the set of that you are trying to define a vector space.
Yeah, because
So,
I'm
yeah,
considering.
they need to be differentiated. Both are t's, and one from the field and the other one from the set that you want to define as a vector space. Right?
Yeah, right.
those
So,
things are not
for-
same T.
They are coming from the same
Same
set.
set.
Numbers, but my
So okay, let me make subtlety here. Yeah. So here, for these two cases, t is the element of the field R, and for this case, t is
you can put a name to that set that you first chose.
this.
Yeah.
Okay,
Either
sir.
name S or what. Or, yeah.
So t is in closure. Okay. So I just defined it in this way. Okay. So I can actually. So I think this will be better if I just changed it. U
Yeah, much better. Thank you.
U U. In the vector space.
We are going to prove that it's not a vector space.
Yeah. Sorry.
So
Right.
let not call it a vector space.
I'm just considering the R bar.
It's a set.
Yeah, it's a set. Okay. Sorry, just saying. Okay. So and infinity plus minus infinity is equals to 0. So is the set R bar a vector space over the real number? Is it a vector space?
set.
Yeah. So these are the operation I defined. Okay. So under this operation, is this which one? This is this is 0. I defined this. Yeah.
That is your definition. So what it uses definition.
So according to this definition, it tells us that infinity is minus infinity is the additive inverse of infinity.
Okay.
Right?
Right.
So
So I'm trying, we are trying to make sense of infinity and minus infinity through this example. But we'll see that it's not possible.
Okay.
Like you said, it's the inverse of infinity. That means it's supposed to be 0. So it should be equal to u. U plus infinity equals infinity.
U plus 0 is u. 0 is the additive item.
Right.
Infinity is not the additive item.
infinity is an element
Whose additive inverse is
minus infinity.
we are trying to establish that minus infinity is infinity's additive inverse.
So what I made was the identity of infinity is u. As
Additive identity means the zero vector. Additive inverse. Do you mean additive
So,
inverse?
okay.
No, identity. But he defined u plus infinity equals infinity plus u equals infinity. That means u is the additive identity.
Then U becomes additive.
Yeah.
Yeah.
Infinity plus minus infinity is supposed to
Then U becomes additive.
Yeah, so what I defined here, it is not actually well defined. And you can show that what you just mentioned, it is another um, way to say. And also, you can also show that. So this is, I can write it like infinity plus minus infinity is equals to 0. Then if I use this, then infinity plus minus infinity plus minus infinity is again 0, right? Because this minus infinity, I can replace it by this. Then if I use the associativity, then this is just simply infinity plus minus infinity plus minus infinity is equals to 0.
So yeah, she's right.
Yeah.
It turns out that infinity is
Infinity is
also another additive identity. But additive identity is unique, right?
Yeah.
They cannot be two
So
distinct additive identity.
So the way I define this, it is not actually possible. So that means this is not actually a vector space. Okay. 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 So so let's start the subspaces. Definition. Let V be a vector space over the field F, a subspace of V is a subset W of V which is itself a vector space over F with the operation of vector addition and scalar multiplication. So this is the definition of the subspace. So what I'm considering is I'm considering a subset of the vector space V, and if this subset W is again a vector space over the field F under the same operation of the original vector space V, which are the addition and scalar multiplication, then we are saying this W, the subset, is also a vector space, and this is the subspace of the original vector space V. Okay, so this is the definition of the subspace. And so let me so to check if a subset is a vector space of the original vector space V, there is three conditions you need to check, and these three are: if 0 vector is in the subspace, this is one. The second one is if it is closed under addition, and the third one is if it is closed under scalar multiplication. These three conditions, if you show that these three conditions satisfied by the subset W, then you can say that W is a subspace of the vector space V. So again, there is a theorem, and the theorem is a non-empty set subset W, W of V is a subspace of V if and only if for each pair U, V vector belongs to W and each scalar C belongs to the field F, the vector CU plus V belongs to W. So if you show that this condition holds, then W is a vector space. Sorry, W is the subspace of the original vector space V, and that's why I give you these three conditions, and can show that actually this condition, if you consider W as a subspace of V, this condition hold. So these three condition, a subset of a vector space V, if these three conditions satisfied by the subset of a vector space V, then that subset is a subspace of the original vector space, right? So, and
So just one query.
yeah.
is this subspace important? Why do we need to define? Is this vector space itself or enough? How does it benefit? Just great layer.
So,
Okay.
so let me try to answer your question. For example, suppose you are looking at R2. R2 means the set of all ordered pairs where each entry belongs to R. That's what we call R2. So in order to see it geometrically, this plane is R2. So suppose that's the origin of R2. This is the y-axis, this is the x-axis, and any point on this plane. So that side, that side, that side, the whole plane is the two-dimensional. I should not say dimensional because we did not define dimension yet, but it's R2, all of it. And using the axioms, you can show that this is actually a vector space. I think it was one of the exercises where you show that it's a vector space. It is a vector space over the ground field of R. The scalars are coming from R, and the vectors are ordered pairs, R. Now, you may be interested in a subset of this R2 of the form of the form where each entry of that subset is of the form 0, u, where u belongs to R. So geometrically, it tells you that you are on the y-axis, right? So I'm just taking this y-axis out and trying to check if it is by its own right a vector space. I may have interest on such thing. Then if you can check that by its own right is a vector space because that origin is there. That serves as the additive identity, and for each 0, u, you will have 0 minus u, which will be the reflection of that point about the x-axis. That is going to serve as the additive inverse of the original point on the y-axis. So you can check that all these axioms are fulfilled and it is also a vector space. Now you can ask, suppose I choose a line parallel to y-axis, like here. Now I'm asking if it is also a vector space. It is not, no? Because the zero origin is not here. So not all the subsets of the original vector space is also a vector space. We are interested in those subsets which also carries a vector space fraction. Those are called vector subsets.
But also just that.
No. So this is an example here.
Now I get it. So you need to define.
Actually, you can show that all the lines going through the origin is a vector subspace. It can be an inclined line going through the origin.
Yeah.
So its equation is of the form of y equals to mx. That is going to be a vector subspace of R. So your the ordered pairs of the form x, comma mx, right?
This is also a vector
So
space.
what is an element of this line? It's of the form x, comma mx, right?
Because this line is y equals to mx.
Yes.
Right?
So you can find that origin is there, that serves as the additive identity, and you can also show that.
So every line going through this origin is a subspace of the original vector space R2. And also I think, sir, there is another motivation coming from the physics, because when we are taking the component in a certain direction, we're considering the subspace of the original vector space. Like if you in physics, if we consider a vector as an arrow, then these two are the subspace of the original vector space, and if you take the component of this will be simply on this axis and this axis, but these axes are just the subspace, and you can show that this is actually the R2 is the direct sum of this R1 plus.
Yeah, but you need to
No, no, sir. I just right. Okay.
Yeah.
So the direct sum I didn't define it. Okay, so so let's show that this is actually a subspace. The subspace needs to satisfy this condition. If this condition satisfied by the subset W, then this is actually a subspace. And how can you do that? If you set W is a non-empty subset of V such that Cu plus V belongs to W, then can you show from here that this is actually what? This is actually the subspace. Yeah. How can you do that? So this U and V are just elements of W. Okay. So for if I consider U belongs to W, and I can write like -1 times U plus U vector plus U vector. This is equals to what?
Zero.
This is the zero vector. So, and zero vectors then belongs to W. That means W contains the zero vector, right? And also, if U vector or V vector belongs to W, and I can take arbitrary constant, then let's just consider C equals to 0 again. So C is the element coming from the field, and I'm considering C equal to 0, then 0 times U, so I can multiply for arbitrary C belongs to F, C times U plus 0 vector, this is equal to Cu, then this is also belong to W, because every form of this,
So you have to express zero.
yeah, zero vector. So this, so I took it as this condition is true. I'm taking this. Okay. So that means Cu also belongs to W, and finally, if I set C equals to 1 and U comma V belongs to W, then 1 times U plus V, this is again belongs to W, that means U plus V belongs to W. That means this set W is closed under addition, scalar multiplication, and the zero element, the zero vector is also in this set W. That means this is a vector space. And so, yeah, this is a vector space by its own right, and but since we are considering W to be a subset of the original vector space V, that's why we are calling it as a subspace.
The existence of additive inverse.
Yes, sir. I already proved it for the vector space, right?
Where?
For the vector space in the last class.
Yeah. So if that condition is fulfilled, for any u vector and v vector in W, that cu plus v is also in W. Does that prove that how does it prove that if u vector is in W, then minus u vector is also in W? You need to check that here as well.
So, sir, 0 is in W.
Okay.
So that means if I multiply this vector, I'm considering, let's say, u belongs to W. If I multiply minus 1 times u vector plus u vector,
No, plus 0.
sorry, like 0 vector, and this is
also in W.
yeah minus u vector, and this is belongs to W. Okay.
So which proves that under this condition, the additive inverse of any element of W is also in W.
Yeah.
Right?
Okay. So okay, so there is
one vague question.
yeah.
So how do you do this elements epsilon, right? So when I write Q is go up Q.
Yeah.
So cu vector plus v vector epsilon or element of W. So do we write X or do we need
No, so this is the theorem. No. So
That is the notation for
Belongs to.
belongs to.
Belongs to what? I mean, like
Belongs
not
to.
V, both belongs to W. Right?
No, the addition of these two guys, that element
That belongs to.
that belongs.
So we don't need to put any parentheses.
no,
No.
I mean, it means that
Is there any precedence in this stuff? No.
no,
This element is element, right?
Because-
second that is just an element as
So-
an element of
So
the set.
that total additive thing is an element, right? So again, that is my understanding.
okay. So there is another very interesting example, and the example is the solution space of a system of homogeneous linear equations so let A belongs to F m cross n and m cross n matrix over the field F, then the set of all n cross 1 matrices over F matrices X over F satisfying Ax equals to 0 is a subspace of F n cross 1. So this problem is saying that the solution space of a homogeneous system actually a subspace of the n plus 1 matrices, right? how can you show that this is actually a subspace? So for the subspace, it has to contain the zero vector, right? So the solution, so ax equals to 0. I'm considering all those x. Yeah.
One other question.
Yeah.
F over M by N is matrix, no?
Yeah.
Field is matrix.
Yeah.
The matrix is also in that field.
No, the elements of that matrix is coming from the field. Yeah.
But field can contain also matrix, no?
No, because every matrix is not invertible. Right?
Oh, that's right.
So for this example, I'm considering the subspace Ax equal to the Ax equal to 0, this homogeneous system. So how can you show that this X, the subset consisting of all these X, form a subspace of these n cross 1 matrices? Okay. So
subspace.
yeah. So what you can do is you can show that this, you can apply this theorem.
Yeah. Okay.
Yeah. And first, what is the solution of this system? Can you tell me what is the solution of this system?
A inverse.
Not actually. So yeah.
Oh,
So the trivial solution is the zero solution, right?
zero also.
Yeah. So that means x equal to 0 is the solution of this system. That means 0 is in this. Yeah. Now let us consider this lemma. And this lemma says that if A is an M cross N matrix over F and B comma C are N cross P matrices over F, then A times alpha B plus C is equals to alpha AB plus AC. Okay. So this lemma is very simple to prove. So what I can do is A alpha B plus C.
What is the alpha?
So yeah, alpha is the element. Yes. Okay. So if I consider the ij element, then this is equal to summation of k. K equals to 1 to n aik alpha b plus c kj, right? But this is simply what? K equals to 1 to n aik alpha bkj plus ckj, right? So this is k equals to 1 to n aik alpha bkj plus aik c kj. Yeah. So then this is simply all these a, I, k, alpha, b, k, j. These are the elements of the fields, right? So I can simply write it like alpha a, I, k, b, k, j, k equals to 1 to n plus k equals to 1 to n a, I, k, c, k, j, and this is a alpha a, b, I, j plus a, c, I, j. Okay. So that means this is simply alpha AB plus AC of IJ, right? So now let us consider two distinct solutions of this system, and this is like x and y are the solution. Sorry, just x1 and x2 are the solution of Ax equals to 0, this system. Okay. So what I can do is I can take the linear combination of these two, like C, just consider alpha x1 plus x2. And now if I multiply this with this, then this is equal to alpha axn x1 plus ax2, right? Using the previous lemma. Is it clear? Okay. But x1 and x2 are the solution of this system. That means, so this is 0, alpha times 0 plus 0, and this is 0. Yeah, sorry. So yeah, this is just the n cross 1 0. This is not the 0. Okay, so that means the solution are in the form of c u vector plus v vector, right? You can write them and still they are in the solution space. That means it forms a subspace of the n cross 1 matrices, right? Okay. Then theorem. Okay. Let V be a vector space over the field F. The intersection of any collection of subspaces of V is a subspace. So I'm considering V is a vector space. Then and then the subspace I'm considering some subspace of this vector space V, and if I take the intersection of all these subspaces, then I will get another subspace. And so, can you tell me what is the intersection of all these lines here?
0 origin.
Yeah. And again, I showed you that 0 is a vector space. And 0 is also a subset of the original vector space V. That means it is a subspace, right? That means when I'm considering the disjoint, like if I consider U1, U2, U3, Un, which are the subspace of this vector space, and all these U1, Ui, Uj, sorry, Uj, they are disjoint. So, sorry. Subspaces are disjoint. No, actually, they are not disjoint.
The zero vector will always be there, common to all.
Right. So they are not actually. The only element
The element common is the
zero vector. That means this is a the U1 intersection U2 intersection U3 dot dot intersection UN contains only the zero vector, right? But we already know that this is a vector space, and this vector space 0 is also a subset of the original vector space V. That means this is a subspace, right? Now, but we are trying to show that if V is a vector space over the field F, the intersection of any collection of subspaces of V is a subspace. Okay. So to do that, let WA be a collection of subspaces of V, and W is equals to A WA. Be their intersection. Okay. So the first thing we need to show that 0 is here. Is 0 in W? Is 0 belongs to W? Why? Yeah.
So origin.
No, I'm not considering the this example anymore.
So this is subspace.
Yeah. So
Subspace is obviously part of the element of 0 is a subspace, right?
no. So I'm considering a arbitrary vector space V. Then I'm taking an arbitrary collection WA. So and then I'm taking the intersection of all these elements. So why 0 is in W? Yeah, because all the subspace contains the 0, because otherwise they are not subspace. That means since every WA contains 0 vector, then W also contains 0 vector, because I'm taking the intersection, right? Okay. So now let us consider u, comma v. These two vectors belong to W. So the question is these two vectors cu plus v, if I write this as this, then is it belongs to W? Is it?
Yes, it does.
Why?
It's a linear combination.
No. Yeah.
Since u vector is in W and W is the intersection of all those W vectors.
Yeah.
So u has to be in at least one of those W vectors, right? Otherwise, it would not be in the intersection.
Yeah.
Yes.
There exists an A for which u is in one of those W vectors.
So
That is the key.
yeah, so it took me a long time to understand why this is because I always thought u belongs to W1, then how can I take the linear combination with some other vector? Because
It's not linear combination. You have to
Yeah.
use the argument that since it is in the intersection,
Yeah.
it has to be in at least one of those constituents.
At least one or all.
all of them.
Yeah,
At least
means-
one of the means all of them.
At least means that you at least have to have it in one of those subspaces. You can have in all of those subspaces.
That means just
Intersection.
yeah,
Then they have to be all of them.
yeah, they are
Otherwise-
in so
Yeah.
so if you consider u belongs to say W1, then u also belongs to W2, u also belong you also belong to W. Yeah. Yeah. Then this is just for e. So I'm considering this is n. So and also v belongs to, since v belongs to W, that means v belongs to W1,
Yes.
v belongs to W2, v belongs to Wn.
Or subspace.
So then if you write Cu plus v, that means this is belongs to W1, this is also belongs to W2 dot Cu plus v belongs to Wn.
Your argument is correct. She was correct. I think I don't know. They have to be, that vector has to be in all of those.
All of
subspaces.
Yeah.
And only then you can conclude that their linear combinations will be in each of those subspaces.
Yeah. So and the theorem is for any arbitrary collection, but it is simple for finite collection. This theorem can be proved for finite collection, and I understand this theorem first using the finite collection, because the first time I I take the two subspace W1
It
and
does not have to be a finite collection.
no sir,
It can
this
be
is
even
any arbitrary collection.
an uncountable collection.
Yeah, uncountable collection. Yeah. So this is the case, and this is the proof of this theorem.
So this way you prove that Cu plus V
V,
vector
yeah.
is in W, right?
Right. Belongs to W, and we already show in our previous theorem that when Cu plus V belongs to W, that means W is a subspace of the original vector space. Okay, so that means the arbitrary intersection of the subspaces also a subspace of the original vector space. Okay. Yeah. So okay, we can conclude here today if you haven't rushed. Okay. Okay, thank you very much.